hands-on actually. Basically, they will learn how to create them for themselves based on all the training that they will get. So this is sort of something that we have planned for the sessions. And today's session is all about ECDSA, and this is a term that comes across very commonly whenever we look out or search for blockchains. And one of the important reasons why this term always comes up is because of the signing and verification part of blockchain that makes blockchain what it is. And we learned and we understood about the cryptography part of it last week, like the asymmetric and the symmetric part, wherein we talked about RSA encryption algorithm, which generates private and public keys. But every algorithm has its own pros and cons, or you can say that it has its own merits that come with it. ECDSA is sort of ECDSA is basically an algorithm. Whoa. ECDSA is basically an algorithm which allows you to generate and verify signatures, and those signatures are what they are called in terms of blockchain. They are called digital signatures. So ECDSA, the term actually stands for elliptic curve digital signature algorithm. So using this, you generate your own public and private keys, and you can use those private keys to sign your messages to be broadcasted. And the person who gets that, they get your public key, they get your signature, they get your signed data. And using all these three, they basically verify whether the message that has been sent, it is sent by that correct person or not, whether the public key that is assigned with that message is the actual person who sent you that message. So those verifications can be done. So today's agenda for this particular session is that I'll just go through some basics of what ECDSA is, and then I would like to show you a quick demo on a small application that I have created. This is basically to give you a small demo about how public-private key pairs can be generated using the ECDSA algorithm, which in itself has two algorithms, the SHA-256 and the SECP-256. These are combined in Bitcoin or its altcoins wherever it is used in blockchain. So we will be seeing how these key pairs are generated. We will see how where signing is done, how verifications are done, and we will also see how a transaction object is signed. It's not going to be any blockchain per se, but it's a logic or the implementation of how they are done. It won't be exactly what Bitcoin or Flowcoin does, but it is, you will get the gist of what it actually does. And then I'll also show you the same demo, but I'll show you last few weeks I talked about the Florine coin Flow web wallet. So I'll also show you in the Flow web wallet how you can sign your messages and send those messages to people, and then at the receiver end how they can verify whether that message is a correct message or not, and they can verify it. So I'll quickly start with my small PPT that I've just created, and if you could just allow the share screen, please. Thank you. All right, please do let me know if you can see the screen, please.
Yes, we can.
Thank you. So this is the session that we have for today. As I mentioned, this is around ECDSA, elliptic curve digital signature algorithm and signatures. So ECDSA basically stands for this elliptic curve digital signature algorithm, as I mentioned. Bitcoin, because it is the first one that started this, but all the different blockchains as well, including the altcoins that we have for Bitcoins, like what we are also using in Flowcard, which is the Flow coin. So they all use this particular algorithm to generate public and private keys and sign transactions on the blockchain, which basically allow us to control the ownership of Bitcoins. So when we say that a transaction, when it happens, it is something which is sent to a person. And how do we know that the transaction that has been sent by a valid user, or whether the transaction that has been sent, whether it's a valid transaction or not? So that's where this elliptic curve digital signature algorithm comes in, wherein every transaction, whenever I want to transmit a transaction, the transaction has to be prepared first, and then it has to be digitally signed by my private key as well, and then I send it across to the person or to the receiver with his or her public key. And to claim the ownership of that particular person must use his or her own private key to claim that transaction. But before claiming, they also need to verify whether the transaction that has been sent is a valid transaction or not. And that is where this digital signature that the sender has added with the transaction is verified. So the public key of the sender, the digital signature, and the hex data of the transaction, they are all uh, together checked and verified and seen whether that is a valid transaction or not by verifying this digital signature. The digital signature allows you to generate your own public private key pairs and use that private key to generate the digital signatures that prove that you are the owner of the public key, without having to reveal your own private key. Because in blockchain, if you reveal your private key to someone, it means you are basically exposing your own address, wallet as well, and all the balances that you have on that address. So it means that if you by any chance if you reveal your private key to anyone, they also can claim the same amount of points that you have on that address, and there is nothing that you can do. So, but in blockchain, since we have to make transaction, we have to make these transactions on the public network, it is required that you have to reveal your identity. But to reveal your identity, you just have to push your private key and the signatures that are attached with this, and the person receiving it, without even having your private key, they can know that this particular transaction belongs to this particular address, or this particular basically this particular address. So that is where these digital signatures come in. The system is used in Bitcoin and all its altcoins to allow people to receive and send Bitcoins. Anyone can generate their own pair of keys and can send or lock their Bitcoins to your public key. Uh, Stealing of these public keys of the coins, or the floating coins, or the Bitcoins, it is not possible, or it is very improbable, because only the person with the correct private key for a particular public key pair is the one who can basically generate those valid signatures to unlock the Bitcoins. So once the Bitcoin or the coin has been transacted and locked using the digital signatures, to claim that back, you have to have the private key, and only then you can basically claim that back. And the only way that this can be stolen, or this can be you can have, or you can access someone else's Bitcoins, is if uh, you reveal your private key, or if your private key is exposed. So if your private key is exposed, it is only at that point in time that somebody can steal your Bitcoin. Other than that, if your private key is safe with you, it's not exposed, if it's not in any ways revealed to someone, then there is zero chance that your Bitcoin or any altcoin can be stolen by someone. So you, in a common scenario, whenever there is a sender and a receiver of a transaction or a message, this ECDSA comes in. This is sort of a flow that happens, wherein we have two users, Tim and Craig. Tim is the sender of the message, and Craig is the receiver of the message. So what Tim does is he uses the message, and he uses his signature to sign the message using the ECDSA algorithm, and generates a message that is sent to Craig. Craig receives the message and basically uses the public key of the sender, the transaction signature, and then the message, whichever message was sent. and he uses all these three elements to basically verify whether the entire transaction or the message is valid or not. If any of those three components are do not match with the original one, then it doesn't work out. So if the public key of the sender is somehow changed in between, the message won't get verified. If the data has been tampered with, the message won't get verified. If the signature has been tampered with, it won't get verified. So in any case, all the three elements which are required for the verification of the message, if any of those three are somehow tampered, then there is no chance that it can be verified. All right. So I'll now quickly show you one small demo that I have prepared for you. And this will allow you to basically have a understanding of how this entire thing works. Just a disclaimer that this is not exactly how Bitcoin or Fluorine coin generate. They have their own salts and different parameters that also go into the algorithm along with the basics of ECDSA, and that's how they create their own public-private key pairs, which are sort of in a format like in flow blockchain. Every public key that you get, it always starts with a character F. In the testnet of it, every address starts with the character O, which is small o. So those hashings and those modifications to the ECDSA have been done at the algorithm level for the different coins to distinguish themselves from other chains or the other coins. Because if it was not done and it was just the vanilla algorithm that was used, then everyone would and all the chains would have similar looking sort of address key pairs, and you won't be able to make out those differences. So this particular demo is just showing you how the ECDSA algorithm works and how we can work on those. So there are three parts of this demo. One is public-private key pair demo, which means that I can give any private key, and that private key is absolutely open to me, and it will automatically create a public key from that private key. And that is absolutely something that is that happens in blockchain as well. So when we generate the key pair, the private key is something that can be used. If you have the private key, you can generate the public key, but if you have the public key, you cannot generate the private key. So it is not a reverse operation that can happen. You can always generate a private key, you can always generate a public key if you have access to the private key, but the reverse cannot happen. So what I will just show you is that if I pass in two different sets of private keys, what are the public keys that get generated out of them using the algorithm that we have. Then the second part of the demo would be signing, wherein I would put in a signature, a private key, a random value, and then get the public key from there. I will put a demo message in there and get the signature. And then I will also verify the signature, whether the signature is valid or not, by passing the three elements that I talked about, which is the message, the public key, and the signature. Those three elements will be passed, and it will tell us whether it is a valid signature or not. The third one is sort of something that happens in a blockchain, wherein you create a transaction, you have a sender, you have a receiver, then you have the amount that you want to send, and then you have the signature of the transaction as a whole, and you create the signature. And then at the receiver's end, the signature is verified. So that is sort of how blockchain does it. So I'll just start with that demo. But before that, I will just quickly run down some of the helper functions that I have over here. And this is something wherein I have created these verify signatures, which is using this sec name curve, which is sec p256k, which is 256 bytes of information algorithm that is being used. So this sec p256k1 and the SHA-256 with ECDSA. These are the two algorithms internally that are used by the ECDSA to basically in Bitcoin, basically to generate and verify the signatures. So I have these two helper functions. One is the verify signature, the other is the get signature. The get signature generates the signature from the private key and the message. The verify signature gets the message, public key, and the signature, and it verifies whether it's a valid signature or not by returning a Boolean value, which is a true or false. We also have one function from wherein we use the get public key from private key, wherein you pass the private key and you get the public key from there. And then there is this small transaction class that has been created to create the that demo for transaction, wherein the sender, receiver, amount, and the signature is basically used. It's a simple data set just to create a similar sort of a view like how we do it in actual blockchains. Then there is this class for point that is somewhere that is used in this get public key from private key, and these are something, the original source comes from the Bitcoin stack exchanges. This algorithm comes from there. So this algorithm basically is the curve of P and the point values, which these are all something which directly comes from Bitcoin's own algorithms. And this has just been ported to C# for our use in here. And this is available across languages. You can have Python, Ruby, Java, everywhere it can be ported out. So, but for our demo, we are just using these pre-created classes just to show you how it actually works out. So I'll just quickly start with the demo and show you how it's gonna work out. So when I run this across, I should get a console opened up as soon as this warms up. Okay, now this is the console that has just come up, and I'll try to share it across two screens possibly. Just share it on this code, and this would be my output. All right, so I'll just okay. So now what I'll do is I'll just step by step pass through these lines of codes, and we will see the output coming up on the right of this. So I'm just pushing in some yeah. So you can see that these console write lines were just put in just to have some context about what we are trying to do in here. We need to find a way to this somewhere where it doesn't. Yeah. So when I put this public private key pair demo, actually I should have just stepped into it. Let me just do that again, please. All right. So I'll just step right into the public private key pair demo and see what happens in here. So in here, if you see, what I have done is I've just put in a private key, and I've just put a random value called 1 2 3 4 5 6 7 8 9. And what I want to do is when I generate a public key from this private key, you will see the private key come up right over here that has been generated. So this is the public key, which is from here till here. You can see that a longish sort of an character string has just come up over here, and this was generated from the private key that I passed in, which is 1 2 3 4 5 6 7 8 9. But if I just change the private key to something else, it's a random number that I've again put in, and then I call the same function again with the new private key, and you will see that there is another private key that another public key that got generated from the new private key that I just entered in, and it's created using the same algorithm that was discussed below, which is this ECDSA algorithm. So using that, whenever we pass in any private key could be anything that you can pass, and that is a string that can be passed, and it basically generates that public key against it. So it's the public key is basically a reflection of that private key using the algorithm. So your private key is basically something which is sort of a variable value which is received by your algorithm, and it generates a public key which is based on that, including the variable value, which is a private key. So now these are the two public keys that got generated from these two different variations of the private key that we have. Again, I would tell you that this is not how a Bitcoin and other blockchains generate the public private key pair. This is absolutely not. The private key is also generated automatically. The public key against it also automatically generated using their own salts and variables which are passed in to create those private keys and public key pairs. So this is just to show you how that happens, but it is exactly not the same way how the blockchains do it, because the private keys in there are not 1 2 3 4 5 6 7 8 9. They have a certain size and limit and number of characters that they use, and that's how they do it. Now what I'm going to do is I'm going to show you how messages are signed using this and how they are verified. So this is the signature demo part of this, and I'll just dive into that particular piece of the code which is in here. So in here you can see that I've again passed in a private key, which is a random number that I have created in here. Then I generate a public key from that private key, and my message that I have put in is hello world. So it's a static message that I have gotten. And now what I'm going to do is I'm going to generate a signature for that message, which is the hello world message, and the private key that we have put in here as a hard-coded value. So using the message and the private key, we generate a signature, and that signature is a long alphanumeric value that gets generated using the ECDSA algorithm. Now I just print out my private key. This is the public key that got generated from there. This is the message that we are meant to send, and this is the signature for this. So you can see that using the message and the private key, this is the signature that we get. Now if later on, if I want to change the private key but the message remains the same, you will see that the signature would change. That is absolutely something that is expected, because for every private key and message combinations, the signature should be different. So if I change the private key, keep the message same, the signature should change. If I keep the private key same but change the message, then also the signature would change. So for every private key and data key pair, a data pair, the signature that gets generated should be absolutely different every time. So now this is the signature that is that got generated for this set of values that we have. Now to verify the signature, what we are passing is the original message that we sent, the public key of the key pair, and the signature. So in here, what you need to notice in here is that this verification of the signature is happening at which end? It is happening at the receiver's end. The signing happened at the sender's end. The sender had access to the private key and the message, and he generated the signature. At the receiver's end, the receiver won't have access to the private key. What he will or she will have access to would be the message that has been sent, the public key of the sender, and the signature that came in as part of the transaction. So what they do is they use all these three values and see whether they all can be verified or not. So as soon as we pass into the verify signature, we see that this is true. If in between I make any small modification to either of these three, the message, the original message, the public key, or the signature that got generated, once the sender has generated that signature for a particular private key and the message, the corresponding public key, the message, or the signature, if any of those are tampered with, it won't verify. You will always have a false that would come up. I will show you that in a quick time in the Flow blockchain wallet itself, how that should work out. So this is how a signature works out, generating of signatures and verification of signatures. The last demo that we have is in terms of transactions. So this is not exactly what do you say, it's not different to what we just saw in signature, but the data that we are signing is different. So previously in the signature demo, what we saw was we signed a static string. Now what we are going to do is we are going to sign a object, and it's going to be an object which is going to be signed. And that object is usually the case where it comes to your blockchain as well. The transaction is created as a, I believe I gave a small demo on the Flow C# SDK as to how transactions are created, wherein the inputs, outputs, and everything is created. The flow data is captured, and then you create a JSON object. And that is a sort of JSON or a class object that is created in here as well, just to show you how it actually happens. And in here, what we are doing is we are creating a transaction object. The transaction is set with a public key that we generated from our private key, which is a hard-coded value. Then we have put in a static public key of the receiver, which is the two public key. Then we just put in a random amount, which is 10, and then we generate the signature or get the signature. To get the signature, what we are doing, as in the previous demo, it is the private key and the message. In place of the message, we are using the entire transaction, that object of the transaction, and the transaction object is converted to a string, and then the basically the signature is generated. And if I look at this now, you will see that this is the transaction signature that got created for this particular transaction. Now at the receiver end, the receiver would have access to the entire transaction, the public key of the sender, and the signature of the transaction. So when I pass it now, verify signature, you will see that it got verified successfully as well, because we did not make any changes in between. Had it been the case, if we had made any small changes to any part of those three variables, which is the public key of the sender, the message or the transaction in this case, or the signature, it wouldn't have been verified at all. Now, as I was mentioning, I would just like to show you in the real blockchain how this actually happens. So I will take the Flowcore wallet for this and show you how to how to see how signature signing works with a certain public key and a given message. What is the signature that gets created? And then what we will do is we will verify that message as well. And to successfully verify, we have to put those exact same three parameters into the verification screen as well, and it will get verified successfully. But what we will see is that if you make even a slightest change in any of those three values, the signature just won't get verified. So we'll just wait for a few seconds. I think it should just get started. So this is applicable to any blockchain. In any blockchain, when you if you want to sign and verify your transactions or any data for that matter, you can absolutely do that. So in Flowcore wallet, this is available in the file menu, and you will see these two options. One is the signing of messages and one is verification of messages. So if I go to sign message, I just need to enter any flow address. So I will just take one of my addresses that I have. I will just copy the public key of that. So the difference between the demo that we saw and in here is that in this Flowcore wallet, it doesn't ask you for the private key. Okay, it doesn't ask you for the private key. It asks you for the public key, which is the flow address. But internally, what it does is because if it asks for the private key, there is a chance that I might expose my private key to someone else as well, and it might get stolen or something. So what they do is they ask you just for the public key, and that public key should be something which has gotten generated on this wallet only. So because I generated this address on this wallet only, it means that the private key is safely kept by this wallet and maintained by this wallet only. So for the signatures and verification in the Flowcore wallet or the Bitcoin Core wallet as well, they do not ask you for the private key. What they ask you is the public key. When you click the sign message, they internally generate the or export the private key or access the private key for that particular public key from the wallet and use that to sign the message and just dispose that again. And it is not shown to users at any point in time, just to keep it secure. So I just put my public key. I will push a message which would say a test message or something, and then I will just click on the sign message. And when I click on sign, you will see that this signature comes in at the bottom, just like our demo, but we did not put in the private key. It automatically got picked up from the back. So now what I'm going to do is I'll just copy this, and there is this verify message tab. In the verify message tab, I will copy the signature at the last place at the bottom. The flow address that I used, I will copy that again. So these are the three values that will be required by the receiver as well, and the message. So the public key, the message, they came in from the receiver, sorry, the sender, and public key of the sender, message, and this is a signature that came. If I click on verify now, it will say message verified because I did not tamper with any of these three things. I did not change the message, I did not change the sender's public key, I did not change the transaction hash or the signature. If I make even a slightest of change, like if I remove the E from the data and try to verify, it says message verification failed. I bring the E back and verify it again, it says message verified. If I change the public key with the slightest changes, I click on verify, it automatically says that the entered address is invalid. Now, this is an invalid address because it does not conform to the algorithms. Now, the other thing that I can do is I will use another address. So let me just quickly copy this sign signature. I'll use another, I'll just keep this in a notepad. I will use any address that I can see. Just see if I have any transaction addresses or not. Or I'll just generate a new address, test address. So what I just want to try is that if I keep everything same, but if I modify the receiver's address, so this is the a new receiver, a new private key, sorry, a public key that I use, but the signature of the data is same, the message is absolutely the same. If the message is same, the signature is same, but the flow address has changed. If I try to verify, then also it doesn't work. If I bring back my address that I used for the verification, for the signing, if I bring that back again by putting the flow address as it was during signing, and if I do the signature in here, everything works again. If I make a small change in my signature, verify it, it says it cannot decode the signature and it would fail. So the crux of the matter is that anything after a signature has been generated, if you modify a slightest, if there is a slightest of change in either the sender address, yes, the sender address, public key, the actual data, or the signature, if any of these three are tampered with, your transaction would never get verified. So that is how this ECDSA basically works at the back end to make blockchain safe and secure. And it allows people to have trust on it, that the transactions that have been sent are actually sent by the persons whom they claim they are. So this is something that we just wanted to discuss today. And that's pretty much it from my side today, guys. And if there is any question from anyone, I would be happy to answer those.
Thanks, Abhijit. Great session. I just had one doubt. So I've been hearing this thing of making bitcoins. There are spendable and non-spendable coins. So does this kind of this key, public private key? They say we can make non-spendable bitcoin as spendable through keys. How does that?
It is sort of that. So in fact, that's a great question, Riti, and I had one small tab opened in my screen that I totally missed, and thanks for bringing this up. So this is a small demo that is available on this this URL, which I am just gonna share on the chat as well. This is a great site to just have a quick look at how blockchain works. So when you say spendable and non-spendable, Riti, what happens is that, say I have got a 100 rupee currency note, and you gave that 100 rupee currency note to me. And what you did is you gave me not one single 100 rupee currency note, but you gave me 10 rupee notes, which total to 100 rupee. Now when that transaction happened, there would have been 10 unspent transaction outputs, which I mentioned in a previous session as called UTXOs. So when you made that transaction to me, there were 10 UTXOs of 10 rupee each that came to my wallet. And since it's a chain, everything started from somewhere, from the mining of the address, it came to you from somewhere, then you passed it on to me. But it just kept on coming, and that became an unspent transaction output that you had. Now it belongs to me, but for you it became spent because you transferred it to some other address. So now if you want to spend those 10 transactions again, those 10 transactions again, the blockchain would say that no, this has already been spent, because future transactions show that your transaction has, these UTXOs have already been spent. And that is where whenever we look at the wallets, you will see that once you do a transaction, either an outgoing transaction or an incoming transaction, spend or receive, until that particular transaction has been mined, your balance always shows that particular amount as a pending balance. And if the miners do not verify that, if the miners say that this is not a valid transaction, they just cut it off from the blockchain, and then your transaction basically gets nullified, and that balance doesn't get transferred. And that's how this happens. So what happens in the blockchain is, there is a concept of Merkle root. So in Merkle root, what happens is, you can think of the transactions as in a computing tree. There is a tree with a root, and then you have the child, or the what we call as leaves. So at the very bottom are all the transactions that we have, and at the every top level, every transaction has a hash. Those hashes are combined to create the hash at the just the higher top, just the top level of that particular transaction. And then these hashes are combined, and every time you look at the blockchain, the Merkle root has a hash which is a combination of all the transactions that has happened since the beginning of the blockchain. So this small screen that you see, this has about 5 blocks. It's not it's a implementation of how blockchain works. So it's a very easy example to understand how blockchain works. So you can see that it has three these elements. This is the block number, which is the block one, which usually the term genesis block comes in. So this is you can think of this as the genesis block. And how do I know this is a genesis block? One, this the number of the block number, and also the this prev value. The prev value in here is 0. It means that it doesn't have a previous hash. It means that it is the first block that got generated. So in here we have the block number, and then we have something which is called as a nonce. Nonce is basically a small random value which is used to create your hashes or signatures randomly. And this is the data that is part of that blockchain. This is the previous hash, meaning the hash of the previous block. But since we did not have any hashes blocks previously, it is 0. And this is the hash of this current block. Now, if I just scroll to the right, you will see that this hash becomes the previous hash for the second block. And then there is a new hash that gets created for block 2. And then the hash of block 2 gets used in the previous hash for block 3. The block 3's hash is used in block 4. The block 4's hash is used in block 5. It means that every hash for a block is an input value for the next block. So if you make any change in any of the blocks, even if it was created quite some time back, the entire blockchain will say that that is not a valid. So if I can just show you that right now, you can see that all the blocks are green. It means they are all verified. If I just make a small change in this block, you will see that they all get red. It means that they are not matching with their previous blocks, and they are just getting unverified. So if I make the change in the first block, all the subsequent child blocks just get unverified as well. But if I make a small change, let's say in the fourth block, then the third block, everything is still verified because that still matches. But from fourth and fifth, it stops working, because now the changes that are part of the blockchain, they are not mined. And now you see that if I make this change, to make this part of the blockchain, I have to mine this. And once it is mined, then this becomes verified. But the other block, that is the next block that got created, it still contains the previous hash of some other block that was mined previously and has changed right now. Now we have to mine it again to match the current block structure. So if I mine this again, you will see that it get verified again based on the current blockchain status. So this unspent and spent things, Riti, this happens through this only. That if I spent, so what I did over here was that I might have already spent something in this block and it got created in the second block, but then I wanted to spend it again by changing my transactions to some other receiver address. As soon as I do that, the blockchain will detect it and say that it's an unverified transaction and it will just fail at the mining process. All right.
Okay. Yeah. So that means somebody can generate a private key to me and make my transaction spendable. That's possible.
If you expose your private key, then someone can. If you do not expose your private key, then nobody can spend your coins on your behalf.
Okay. And I think Sogato had a question. He has written, can different public keys be generated for a particular private key in any exceptional case?
So no, Prasogato, for a particular private key, the public key is always the same because it's based on the algorithm, and the algorithm always generates the public key based on the private key. Yes, in some of the wallets there is a concept of a master key and the secondary keys. So usually what happens is in the Flow Core wallet as well, there is one master key that is created, and if I remember correctly, I showed you in MetaMask, there is a 12-word key sequence that is used to keep your private key safe in case you forget it. If you have access to those 12 words, you can again regenerate your private key. So in there also what happens is that there is one root key that is created and it has its corresponding public key. But there can be subsequent private key public key pairs that can be generated from that root private key or that key pair, and then that can be used to generate n number of key pairs that you want, and that is exactly what happens in all the different wallets as well. But for one private key, the public pair, the pair is pretty much the same. Any other questions, anyone? All right.
Okay, if not, then let's, you can talk about the next session, Vijay, whatever.
Yep. So the next session, I believe, is on the next session is on how blockchain works. So till now, what we did is we talked about all the technical parts of it, like the wallets. We understood what wallets are, what cryptography in different algorithms are. From next week, my friend and colleague Ritvik would be taking a few of the sessions for you, and he would talk to you about how blockchain actually works, how the Genesis block gets created, how the blockchain actually works, the hashing and the cryptography that we talked about, how they're implemented in blockchain. Then he will also talk about the different types of blockchains like private, public, private, and permission blockchains. So those are some of the basically the blockchain and its core fundamentals. Those would be talked about in the next few sessions by my colleague Ritvik.
Great. So thanks for that, Abhijit. And I've also, so if you've missed any previous sessions, you can go to our YouTube channel on SkyPicast and see the videos, guys, and catch up on what we have done so far. And then you can start also joining us from the next session onwards. So every Sunday we meet at 11 o'clock. I've shared the link on the chat box, so you can save that link with you, and we'll add the previous sessions, more previous sessions to it. Okay, so thanks Abhijit. Thanks for the session.
Thanks, Rudy. Thanks, everyone. Thanks for joining.
Everyone, thanks for joining.
All right. Bye-bye.
Bye-bye. Thanks. Okay, Ujjwal has something to ask. I think.
Yep.
Abhijit,
Yeah, Ujjwal. No worries. Hi, Ujjwal. Please feel free.
Hello,
Yep.
am I audible?
Yeah, you are.
Yeah, so my question is कि अगर मुझे $1000 का बिटकॉइन खरीदना है इंडिया में,
Mhm. Mhm.
तो what is the procedure normally, except P2P?
If you want to buy bitcoins,
Yeah.
yeah, you can buy it from any blockchain Bitcoin exchanges that are. So Bitcoin के लिए ऐसा है उज्जवल कि there are multiple exchanges that trade in Bitcoins. So in India
Okay.
there are different like WazirX, CoinX, CoinDCX, ZebPay. These are all
तो
registered.
वहाँ पे हम लोग अपने कार्ड से जाके नहीं खरीद सकते, right?
You can these registered exchanges that are operating in India, they are some you can transfer the INR into their accounts. There is a process that is there for depositing into their wallets, and from there you can buy the coins that you want. But do be mindful that crypto exchanges do have a tax associated with that from Indian government.
Tax in what level? Like
Yeah. So
30%?
whenever you trade in cryptocurrencies, I believe Indian government has a tax of 30% added whenever you do a transaction, and when you get those profits, there is a 30% tax that you have to pay to the government.
Profits or the amount?
The profits. And a
Profits,
TDS of 10% is deducted on the amount that has been transacted. So the taxation is not very clear right now, but whichever exchange you want to buy or transact them, there are different FAQ sections that talk about those taxes and stuff, and you can just go through them before doing any transactions there.
Okay. Okay.
Yeah.
Thank you.
All
Yeah.
right. All right. Thanks, everyone.
Thank you.
Thanks.
Thank you.
Thanks, guys.
Thank you.